Thank you, and I have to say it was really a terrible sacrifice to spend a weekend in Sydney. So, you have to be really grateful to me to have made that sacrifice. So, well, thanks for the invitation, and thanks for coming here. And so, yeah, today I will talk about going towards user-adaptive visualizations. And before going into the details of this particular piece of research, I want to give a bit of an overview of my general research area, which is in user-adaptive interaction. User-adaptive interaction is an interdisciplinary field that combines research in artificial intelligence, human-computer interaction, and cognitive science with the overall goal of creating intelligent user interfaces that are better at providing interaction that is personalized to the user by being able to kind of model and track in real time specific user needs, preferences, and other individual differences, and adapt the interaction accordingly. Now, in order to be able to adapt to user properties, obviously, you need to be able to model these properties somehow. And this happens in the component of an adaptive user interface that is known as the user model. And people, this research has been going on for a long time, and people have been working on modeling things such as user goals during the interaction, knowledge, behavioral regularities, preferences, and even things a little bit more esoteric such as affective states, cognitive load, and so on and so forth. Obviously, these are variables that can often be, there are hidden variables with respect to what the information from the interaction can tell us. So there is a lot of parts of the research in user-adaptive interaction is about how to infer these user properties based on information that you get from the interaction with the interface, going from the basic interface actions, but also having to try and add additional sources to be able to fill the gap between what we can actually see in terms of what the user is doing and inferring these high-level properties. And people that look at things like recording speech, using gestures, body movements, and the dots there are to say that there's many other things that I won't have time to list here. The point is once you have some information about the user that, some of the things that we have in this box, the idea is to provide personalization and adapt the interaction, and there is a variety of ways of doing that. For instance, people are working on providing personalized help on a specific task the user is trying to perform. For example, if it's a learning environment, provide didactic hints that help the students learn better. But even other forms of visualization, personalization entail, for instance, changing the interface layout to better accommodate the user needs, or tailoring and changing how the information, the content is actually presented, or even recommend specific objects or actions to the user during the interaction. And again, these are those dots because there are several other things that one can do to personalize. In general, the main three initial steps that need to be done in order to build a user-adaptive system include these three things. First, it's important to understand what are the user characteristics that are worth personalization. Building personalized system is not easy, it's a lot of work, so you want to make sure that you're focusing on the individual differences that actually impact performance with an adaptive system, okay? And some of these characteristics might be obvious. For instance, if you're devising, again, an intelligent tutoring system that tries to teach something, taking into account and modeling user knowledge, it's an obvious thing to do. But there are other things such as, for instance, emotional reactions that you might not necessarily know a priori what are the emotions that are important to recognize and track. So important thing is to try to investigate which are the user characteristics that make a difference and are worth exploring for personalization. The second step is understanding why these user characteristics impact performance. Because if you understand that, you might be able to understand how to provide personalization. What are the things that you need to change in the user behavior that could help improve the interaction with the system? And lastly, is it possible to build user models that can predict in real time the characteristics that have been identified to be important for adaptation? Okay? So this research in user-adaptive interaction has been around for more than 2 decades. Some examples that you might be aware of include recommender systems. That is one of the main examples of research in user-adaptive interaction. Intelligent tutoring systems is also a large field where these ideas have been investigated and applied. Smart homes. Some of these things are picking up and becoming more and more popular now because of all the AI advances that have triggered the interest of Google and Amazon, and they're creating all these devices for smart living. It's been applied also for entertainment, for instance, applications where you have intelligent game agents that help make an electronic game more interesting and engaging, assistive technology, so on and so forth. A field in which these concepts of user-adaptive interaction have not been investigated much is information visualization, okay? And information visualization is something that is becoming more and more prominent in our daily lives. Up to a few years ago, it was a very specialized field where researchers were trying to come up with fancy visualizations to represent complex data for mostly professionals, okay? But these days, since data is collected about almost every aspect of our lives, and there are lots of devices and apps being created to show us trends and patterns based on this data, visualizations are becoming important in our daily lives, not just for professional situations, but also for personal usage. And the thing is, so more and more people, without necessarily a deep background in how to understand complex visualizations, need to deal with this visualization. But the way visualizations are designed in the information visualization field still tends to be what's called one size fits all. That is, researchers look at the type of data that is available, at the type of tasks that need to be supported, but they don't look at potential differences in users' populations that might impact which visualization would work better. And however, there is increasing evidence that individual differences matter. Very dense slide, you don't have to read the text, just look at the red stuff that essentially says what previous research has shown could have an impact on visualization processing, and these are things like preferences, domain expertise, some cognitive abilities related, for instance, to spatial processing, perceptual speed, visual working memory, and people even found that there are some personality traits that impact how people process visualizations, including this one at the bottom, locus of control, that essentially measures one's tendency to believe that one is in control of their own circumstances as opposed to fate is in control, okay? And there have been, studies showing that this personality trait affects how people work with specific types of visualizations. So, point is, there is a great need and potential for personalization in this field. It hasn't been really this problem hasn't been looked at. And so this is one of the reasons why, with my team, we had started thinking about user-adaptive visualizations. And the ways in which personalization could be provided, adaptation could be provided to people to work more effectively with visualizations are these two categories. First, one can think of providing personalized support to work with a specific visualization. There is only one choice, and you notice that a person might have been having problems processing a specific visual display. One can think about providing interventions and adaptations that can help, for instance, focus on the right things in this visual display. An alternative visualization, an alternative way to personalize would be to have perhaps alternative meaningful visualizations for the same task, and the point would be trying to understand what is the most suitable visualization for a specific user and recommend that, okay? And in order to do that, we're working on understanding how to build user models that capture relevant characteristics that could drive these forms of personalization, and looking at which input sources we can use to derive these abilities that could, for instance, given what I showed you earlier, could relate to perceptual abilities, expertise, if the user is confused while looking at the visualization, the cognitive load. An interesting point is that if you need to have information during the interaction, some visualizations are interactive, but some are not. And in any case, the main source of information is how users are looking at this visualization, okay? So there is no way to kind of go without looking at eye tracking technology to be able to capture information and user attention, okay? So this is what we're focusing on. So going back from the general slides on what are the steps to build user-adaptive interfaces, this is just repeating that to say that if we're working with visualizations, which is a new field where there hasn't been much research on how to provide personalization, it's even more important to investigate these three questions, such as what are the user characteristics that impact how people look at visualizations, how these characteristics actually affect behavior, and can we build user models that can predict in real time these user characteristics, okay? So we'll just skip this for now. What I will do now for the rest of the talk, I will first show you some results that we obtained looking at applying these three steps to visualizations that are based on bar charts. Then I'll look at another example with more complex setting and visualizations, and then I'll discuss some research directions, okay? And if you have questions as we go to clarification questions, like deep discussion questions, maybe we'll keep them for the end. But if you have clarification questions, please feel free to ask me. Okay, so bar charts. Why do we focus on bar charts? Well, charts. Because we were wondering, bar charts are the simplest type of visualizations that are well known to be effective. They're very widespread. I just put up here some examples of, magazines and textbooks, and newspapers use them all the time. This is a visualization based on bar charts showing that in dashboards for education, bar charts are the most used visualizations to show teachers and users information about what's happening in the classroom. And, well, if they're so well known, maybe everybody knows how to use them, and there's no need to provide personalization. So, is that true? That's the question that we asked ourselves. So, we wanted to look and apply these three steps to understanding if there is need for personalization and how that would be for bar charts. So we ran a study where we had 62 participants. So it's a within subject design. They were tested for a variety of user characteristics that we thought could impact how they process bar charts. Then we gave them a battery of visualization tasks to be done with bar chart visualizations of varying complexity. I'll show you what they are in a bit. And these come from a well-known taxonomy of basic visualization tasks that is used all the times in information visualization. And then in the end, they took a questionnaire on how they liked working with the visualizations, which one they preferred, and so on and so forth. Throughout the main part of the the study, when they were looking at the visualization, their gaze was tracked with a Tobii TIA-120 eye tracker, and I'll give you more detail about that in a couple of slides. First, I want to just show you a little bit what are the user characteristics that we were looking at. So we looked at these three: perceptual speed, which is a measure. These are well-known psychological constructs. Okay, we didn't make them up. They're coming from perceptual psychology literature. Perceptual speed is a measure of speed when performing simple perceptual tasks. Visual working memory, it's a measure of one's capacity for storing and manipulating visual information, such as shape, color, orientation of objects. And verbal working memory is the counterpart, so measure of the capacity of manipulating and storing verbal information. We also looked at this locus of control personality traits, since others had found that it could have a difference, that it could make a difference in visualization processing. I was actually curious. For me, it's hard to believe, so we decided to test that as well. These things can be tested with tests that are available. There are psychology tests. They're well established. And in fact, if they are collected, we summarize them in this website if you're ever interested in looking at what these tests look like, how long it takes to give them out. There are some there on paper, some there online. This is a good summary if you're interested in going a little bit more detail about that. And then we also tested for visualization expertise. This was self-reported on a 5-point Likert scale where we asked users how often they essentially use and interact with bar graphs, okay? Just to have a sense of how familiar they were with this type of visualization. And it was actually quite a spread, so it wasn't everybody uses a bar charts all the time. So the studies users were completing 2 types of visualization tasks. For instance, and we wanted to give them a simple task and more complex ones to see if task difficulty would impact our results. So simple task is called retrieve value. And what it means is that questions related to this task will ask users to identify specific value in the data set. For here, this is a data set that shows a variety of students' scores on different courses, and they are compared against the black thing here, which is the average in the course. Example question for this task type is Lindsay's grade in chemistry above the class average of that course? So essentially, one needs to identify chemistry and compare Lindsay's grades with the average. More complex types of tasks involve this compute derived value task and involves essentially retrieving maybe more than one value and also do some operations with it. So an example here is in how many courses are both Lindsay and Kylie above the class average. So obviously one needs to go look at all the different bars and count, okay? And again, these are labeled as simple and complex in this visualization hierarchy for visualization tasks that comes from the literature. And last thing, users were, as I said, the user gaze was tracked with this eye tracker. The eye tracker is embedded in this monitor. So there's a camera here that detects your pupil and just keeps track of the movements there. So it's completely non-invasive. I'm just going to show you a super quick clip showing the user there, not touched by anything. And these are little dots that show where the user is fixating and for how long, the size of the dot represents for how long. And then the red lines are how users are transitioning from one position to another on the screen. Okay, so the data from this study, we used it to answer the questions related to the 3 steps that I mentioned earlier. So the first one, we want to understand what to adapt to. So which individual differences impact user performance in answering questions on these visualizations, okay? Where performance was measured as a combination of time and accuracy in answering these questions. And I'm just going to give you a sample of results. They're much more complicated than what I'm showing here, but just for the sake of time, if you are interested, there is a reference there, and I can give you more details later. But essentially, for instance, we found that users that had lower measures from the test that they took on perceptual speed, visual working memory, and verbal working memory, when they had lower measures of these abilities, they actually performed worse. And all the results that I'm showing are statistically significant, otherwise I wouldn't show them, okay? So there is a data analysis formula in the paper described. And and this happens when the tasks are more difficult. So when the tasks are of the easy type, these individual differences don't make a difference. They kind of perform all the same. But when the tasks get difficult, that's when measures for these perceptual abilities start playing an effect, having an effect, okay? So what's the implication for personalization? Well, it is, at this point, seems that users with lower cognitive abilities, these 3, can benefit for support when the tasks get hard, okay? The second thing, which type of support? So this goes into the second step in the general methodology, that is understanding how these individual differences impact behaviors during visualization processing. So we're looking at how these characteristics impact how users are paying attention to different parts of the visualization. And in order to do that, we look at these gaze patterns. They're tracked via the eye tracker device. And just a quick summary of how that is done. So the eye tracker, as I mentioned, gives raw data that consists of position of the fixations and duration of the fixations. So general measures that can be used include number of fixations produced while performing a task, fixation rate, the duration of the fixations, and there are also measures related to the length of the transitions between fixations and the angle between the saccades that essentially tells how the user is sort of like moving across the visual space, okay? These measures can be taken over the whole screen, or one can also identify specific areas of interest on the screen. For instance, for a bar graph, areas of interest are the top part where the differences in bars are reproduced. The information about what are the groups, the different data that we're looking at, the legend that allows you to do the mapping between data points and the bars, the question, and the input area, okay? And once you have these areas, you can get similar measures just related to the areas. So proportional number of fixations in each of the areas, proportional fixation time, and even things such as transitions between AOIs, okay? You can go very complex and do transitions across several AOIs. Here we kept it simple, and it's just transition between any two, okay? And we look at measures such as sum, mean, and standard deviation of this to characterize each user's attention to the screen, all right? So what we did in this part, to understand how user characteristics impact these gaze properties, we actually ran an analysis where we ran a statistical model to see if user characteristics change or influence how the different measures on gaze behavior work out. And again, the analysis is described in this paper. And again, I'm going to give you a little bit summary of some of the results just to give you a sense of what things you can find when you do this kind of analysis. So for instance, we found that low perceptual speed users spend more time, more effort in processing labels. The labels that are at the bottom of the graph and show what are the names of the different groups. So more fixations, more transitions to that area. And this effect gets larger as the tasks get more difficult. So that's where, and the low perceptual users, as we said before, tend to be slower. So this is an indication that this could be an area in which they are kind of falling behind a little bit, so to speak, with respect to high perceptual speed users, because they get caught into going back and forth and processing, needing to process the labels longer. So in terms of implications for adaptation, one should consider looking at ways to support label processing for low perceptual speed users when the tasks get hard, okay? Another, just to give you a sense, we also found that low verbal working memory users tend to spend more time processing the verbal components of the graph, like the question, again, the labels, which is kind of intuitive because they have lower verbal working memory, but it's interesting to see that you can detect these differences by looking at the gaze data, okay? And low visual working memory users, we found that they can spend more time processing and going back and forth to the answer area, where you put your answer in, which we think it's an indication that they also need to spend more time doing the mapping between what's the answer that they can retrieve from the bar graph and what is the actual answer that they have to produce. So again, the general point here is that there are different user types, and they seem to be stuck in different parts, different aspects of processing a bar graph. So it's important to understand these differences and think of adaptations that target the specific problem areas for each of these users, okay? Okay, but can we predict? So it's important to understand when the user is doing an easier or difficult task, because when the task is simple, it doesn't look like they need any help. What happens if you need to look at when the task is difficult? And we found that these three user characteristics could be important for adaptation. Can we predict them in real time? So can we build these user models that could, in real time, detect if a user is a low perceptual speed user, for instance, that needs help? So we try to build predictors using machine learning techniques based on the eye tracking data, because that's all we have here. There is no interaction whatsoever using mouse or keyboard features. It's all based on looking. So just very quickly, the classification experiments here relate to being able to build machine learning classifiers that can predict complexity, so if the user is doing a simple or a complex task, and these cognitive abilities, okay? And we created these categorization classes by splitting users in high and low measures, simplistic, otherwise it could be too difficult for machine learning, but we use a median split on the test measures to divide users in high and low levels for each of the three cognitive abilities. There's some quick details on the machine learning, but more it's in the paper. But essentially, we use the simple logistic regression algorithm that is from off-the-shelf package, Weka. What I want to spend a little time on is how we actually ran the evaluation. We wanted to see how much data from the beginning of the interaction the classifier needed to see before being able to do any prediction on these things, okay? So what we did, we built classifiers for incremental stretches of data, so 10% of the gaze data from the beginning of the interaction, 20%, 30%. And what you'll see next is this graph that shows how accuracy evolves with amount of data that is fed to the classifier, okay? And it's always, in machine learning, you always, sorry, I don't know exactly how much machine learning background you have, but you always want to compare your classifier with some obvious choice. For instance, this case, majority classifier that always predicts the most likely class, okay? Ask me if you have questions about this. So this graph is the one that shows how classification accuracy for task complexity, easy or difficult tasks, evolves with the amount of data that is fed to the classifier. This is the accuracy line, okay? So the statistical analysis shows that the classifier's accuracy is statistically higher than the majority baseline. And it's interesting to see that the accuracy increases as the classifier sees more data, but already from quite early on, the classifier beats the baseline and the accuracy is reasonable, okay? Meaning that somehow when the task is more difficult, the differences in how the person processes the graph come out right away, okay? So for predicting cognitive abilities, so each of these is a graph for one of the three: perceptual speed, visual working memory, verbal working memory, and again, the baseline. So statistical analysis of these accuracies over time show that each of these classifiers, again, have accuracy that is statistically higher than the baseline. That's good news. Another interesting point is that the peak of the accuracy for these cognitive abilities is never 50% of the data. It doesn't necessarily get much better as you give more data to the classifier, which probably means that main differences in attention that are influenced by these perceptual abilities happen at the beginning of the interaction. That one can do in improving the quality of the machine learning. And there are other data that one can include and get from the eye tracker, for instance, pupil dilation, head distance from the screen, that we couldn't use in the study for reasons that I can explain if you're interested, but that could improve the accuracy, okay? I'm gonna skip this for now. So just a summary of what we've seen so far. So we confirmed that even with simple or at least well-known visualizations as bar graphs, individual differences matter. They can impact how someone is successful in working with a visualization. These differences affect attention to different elements of the processing of bar graphs, suggesting that it's important to look at adaptation that targets the specific elements that are problematic for the different groups. And eye tracking is a promising data source for predicting the important characteristics that we need to track, including task difficulty and these abilities. What I want to say is that we obtained similar results with other bar graph-based visualizations. I won't have time to present all the results here, but these ones that I showed you is not just a one-shot, kind of lucky. There is evidence that these results are quite general across visualizations that are based on bar graph design. But we also wanted to see if we can go and look at visualizations that are a little bit different. And in a more, also looking at more realistic tasks. And specifically, we wanted to try to generalize previous findings to other types of visualizations. Here we're going to be looking at maps and something called deviation chart. And I'll show you what it is. Adding a more complex setting where users can interact with the visualizations, and giving users tasks that are a little bit more realistic, because the tasks that I've showed you before are very much, lab-driven, sort of a little bit contrived, that don't, tasks that are not really related to the user experience. So we're using for this a commercial, we have a project with a company in Vancouver that has created this platform called MetroQuest that are selling very well in North America, bought by policymakers and other people interested in designing decision support systems that help the public become aware of difficult decision-making problems related to environmental policies. So I'm going to show you how this interface works, just with the example that we created for our own study. And essentially, the decision-making here relates to building additional public transport to campus in Vancouver, similar to what's happening here with all these nice tracks being put everywhere. So there is a big debate on how to improve transportation, and there are 3 different alternatives that have been discussed forever. Things that have been discussed in the news, big controversies. So it's something that people are really sort of like aware of. And I'm just gonna play this.
The MetroQuest interface is designed to guide the user through the process of learning and comparing 3 proposed transit scenarios in the city of Vancouver. Screen 1 welcomes the user and provides background information about the overall transit project. Screen 2 helps users select and prioritize which indicators will be used to compare the different transit scenarios. Here, the user selects travel time savings and costs as 2 of the indicators they feel are important. Screen 3 allows the user to learn about each transit scenario using 2 different visualizations. First, on the right, the deviation chart shows a visual summary of the values of all the indicators. The prioritized indicators selected during Screen 2 are displayed at the top. A green arrow indicates that travel time savings will be improved, whereas the red arrow indicates the cost will get worse. Second, a map on the bottom shows the proposed transit route. The indicators are also plotted on the map. For instance, travel time savings are shown as numerical values at various stops along the road. In practice, the user can compare the 3 scenarios by switching among the 3 paths shown at the top. The user can also provide a rating out of 5 stars for each scenario. Screen 4 records basic demographic information and provides pointers to stay involved.
Oh, that's it.
The MetroQuest.
No, that's good. Okay, so a couple of things to focus on this is that, so you saw that the visualizations are a little bit little bit more complex than the ones that we have seen before. There's 2 of them. They are designed to be kind of complementary. You can also make the decision just looking at one of the 2, but the company has done a lot of work. They have visualization experts as part of their staff. They've done a lot of work in trying to understand how to provide rich information, both using by putting together these maps and deviation charts to support the comparison, because comparison is important when you're trying to decide which scenario is better, right? So they've been working at this for a long time. As I said, it's a very successful product, it's bought, but the company came to us because they felt that still, for some of their users, this is too complex. These things are used in situations like public shows, and specific events where you might have a kiosk with your MetroQuest application. Users go, play with it for 5-10 minutes, and then they leave. They generate their ratings, they get exposed to the problem, but it's really a walk up and use system. So it has to be as intuitive as you can make it. It's used by all sorts of people, and for some of them, these 2 visualizations are hard to digest, okay? So that's why they said maybe we can try to find ways to personalize so that we don't have to dumb it down for everybody, but we can try to make it simpler for those who need it to be simpler, okay? So in order to understand how to personalize, we ran a study with 166 users to investigate those 3 questions that I presented already a few times. And what we looked at is we tried to identify in a battery of 10, we had a battery of 10 different user characteristics, which ones impact performance with the MetroQuest visualizations, how that happens, and can we model them in real time, okay? So I'll skip the list of all of them. I can discuss them later if you're interested. I'll just give you the results. So the participants were from the community that is most directly impacted by this project, which is the community, the UBC campus community, which involves obviously students, but there is a huge residential area and people live there and they don't work at UBC, they don't attend UBC, they just like to live there because it's a nice place. We still track the gaze of our users with this TOBI tracker, and users completed at the end of the study, of their session, they completed a questionnaire. Would they rate usefulness of each visualization, which one they preferred, and also they gave ratings for how confident they were in the ranking that they gave on the 3 scenarios at the end of the interaction. And these are what we're going to use for performance measures because it's a decision-making problem. There is no obvious quantitative measure of performance that we could build at the end of the interaction because there is no obvious outcome other than the rating that they generate, okay? So the analysis that we did before, how individual differences impact performance with the bar graphs, there we could use performance measures and how quick they were answering the questions. Here, we just looked at how the individual differences impacted their ratings for the different visualizations, their confidence in the decision, and so on and so forth. So the details of the analysis are in this paper, published last year. But what we found is that of the 10 individual differences that we tested, 5 had an impact on user experience on at least one of these measures that we collected. And examples, and this, again, sorry, all these characteristics are still, can retrieve them in the website that I showed earlier. So an example of what we found include, for instance, that users with low, so we used the 3 that we had, we tested 3 user characteristics that we had tested before: perceptual speed, visual working memory, verbal working memory, and they were found again to have significant impact on performance. The other 2 that came out are more related to processing spatial information with maps and the deviation charts. So spatial memory, it's a measure that gives the capacity for storing and manipulating spatial arrangements of objects. And visual scanning is a specific measure of one's ability and speed in locating objects in a surrounding, in a defined surrounding. And what we found, for instance, all of them had an impact. I'm just going to list 2 related to spatial memory and visual memory. So users with low with low spatial memory found the charts less useful than users with high levels of this ability, and users with high levels of visual memory preferred the charts over the maps. Okay? So, as before, the fact that we found this impact led us to believe that it's important. These are two abilities that might be useful as the focus of personalization. Okay? Examples that could be considered include, for instance, allow users to provide help to process whichever of the two visualization they didn't work very well with, okay? For instance, for low spatial memory users that didn't like the charts as much, one could try to simplify them by providing fewer factors, adding visual cues to understand what's happening with these charts. Or one could even say, well, perhaps we could also allow users to, or suggest to hide the chart if they want to, because these two visualizations, you can still work with only one. You can still find all the information that you need to rate the different scenarios. These are alternatives, okay, possibilities. And for users with high visual working memory, they didn't like the maps as much, so one could think of adaptations that help them process the maps. For instance, showing simpler maps with less detail, or also the other alternative, allowing for ways to hide the map. Okay? Now, before we talk a little bit more about how to deliver these interventions, we want to still see if it's possible to predict these abilities in real time, because that's the other third step that we always need to look for. And again, the detail of the machine learning are in this paper, but essentially it was, as before, we split users in high, low levels of all the 5 abilities that were found to be relevant using media split, used eye tracking features to build the classifiers, and again, for 4 out of the 5 abilities that we wanted to track, except for verbal working memory, for 4 of them, the classifiers, as before, had higher accuracy than the majority class baseline. Best accuracies are obtained by these classifiers after having seen between 10 and 50% of the data, similar to before. So it shows that it's important that you can pick up these abilities quite early on during the interaction. That leaves time for personalization. If you would have high accuracy only in the end, it would not be very useful to provide real-time personalization. The accuracies here are a little bit better than before. In this experiment, we actually could use also from the eye tracker information on pupil dilation and information on head distance from the screen, which is something that helps get information about what they're doing as they're looking at these visualizations, okay? So what's next? Well, you might want to track for these lower level, track users and detect when they have these lower levels of these abilities that we found to be relevant, and then generate interventions to help them, such as suggest to a low spatial memory user to hide the map, for instance, if it's too confusing for her. Or one could always say, well, all this talk about user-adaptive personalization, where is the machine doing things for the user? Couldn't we just make it so that users can customize by themselves? For instance, we could just provide tools to allow them to hide the visualizations when they don't like them, okay? There's a lot of talk, HCI, that empower the user and just provide tools to customize the information and the details, how they interface, how they like. So we actually tried this just to see if we could see how often and how well users customize when they have the opportunity. And we built a variation of the interface that I showed you earlier with these little buttons that users can click to hide either one of the two visualizations, and if they click on it, then this will become show, so they can bring it back if they want to. It's not like done and that's it. So we ran a study with 46 participants, and with this interface. If you want to see how that works, there was actually a link to a demo, but it does exactly what I just said. You just click on the button and it hides the visualization and you can bring it back. I won't go into all the details of the results. This is something that we're just submitted for publication, so I didn't have, at the time that I made the talk, I didn't have all the results in a good shape to present the details. But essentially, in the nutshell, what we found, if of the 46 users, only 15 customized, okay? And just a minority of these said that they didn't customize. We asked them why at the end of the study. When they didn't customize, we asked them why they didn't do it. Only a few, I think 3 or 4, said that they were not aware that they could customize, and so that's why they didn't do it. The others just said, no, because I thought it made sense to have both visualizations. One said, I didn't like the visualizations anyway, so customizing wouldn't help. But the important thing is that we found, the analysis that we ran shows that some of the users who did not customize, that impacted their performance with the system. So if they had customized, for instance, if they had hidden the visualization, they would have had better results with the interaction. And this shows that giving user control is important, is crucial, should always be an option. However, it's also important to have ways to have the system provide support for those users who are not keen on customizing or not used to customizing. And our results here are not the first ones that show that customization doesn't work because users don't engage in it. There are many, many studies in HCI showing this. This is just the first study that does that in the context of information visualization. But other than that, the results are not a surprise, okay? So in general, as a summary of what we got so far, visualizations are becoming more and more prominent in our daily lives. There is a huge potential for personalization. User-adaptive techniques can help. We're building up this evidence that we can identify which are the characteristics that make a difference, how they impact processing. We can track them in real time with some reasonable accuracy that we can work on improving. And so there is a lot of exciting work now to be done on how to provide effective mixed initiative support. Mixed initiative is a technical term for saying that you have ways for the user to do the personalization, but it's also supported by the system. So it's a dialogue between the system and the user on how to best personalize, okay? It's not the system jumping and doing things behind the user's back, and it's not just let the user do whatever they want without any support. And obviously, this is just, we just have scratched the surface of the work on this work, because we just looked at a very small fraction of possible visualizations and how they could be used. So there's a lot of work that can be done in general, trying to see if these results generalize to other visualizations, other tasks, other users. And I just want to, I'm going to leave it 15 minutes for questions, but just a little bit to show you how what we're doing in this area. We're trying to do a lot of work on how to, we are currently working on understanding how to provide effective mixed initiative support, okay? For instance, we've done studies showing how highlighting interventions can help processing complex bar graphs. For instance, and this, if you remember my initial graph on how to personalization could be provided, it's in the camp of providing adaptive interventions on a given visualization to improve the processing of that visualization. So what we did, there was a study where we tried 4 different interventions to highlight bars that would be relevant to understand the specific trend in the data. And we looked at these 4 different highlighting We didn't make them up. They also come from a paper that is quite well known in information visualization. So it's like trying to bold the bar that it's important, de-emphasize the bars that are not important, have reference lines that help make comparisons for things that you want to focus on, and connected arrows are also another way to highlight how to make comparisons when needed. It's a very complex study, so I won't be able to go into the details, but in a nutshell, what we found is that bolding and the emphasizing are the best way to highlight when among the four that we chose. And they work better than no intervention. So that's the important thing, because you could say, actually, all this, is not true. Providing this intervention doesn't really help. User just can be confusing, can be disturbing for the users, okay? But in this study, we actually had a control where no interventions were there, and performance of the users with the highlighting done with bolding and the emphasis was better, both in terms of performance, so how quick users were answering questions on the tasks that we had in the study, and also how they liked the interaction. So this is a qualitative, self-reported measures of usability and ease of use matched with the objective results on quantitative performance. What we're working on is to include this, this way of providing guidance to attention to bar graphs. We are applying it to help users process, and this is in the space of applying this methodology to different tasks and visualizations or applications of visualizations. So here is magazine-style narrative visualizations are essentially documents where there are visualizations, okay, and there is text telling stories and describing aspects of the data shown in the visualization, okay? And the main point is that often, so this is just from an Economist article, you have this graph that shows different trends in increase in the global car industry for different countries. And the article, the full article is this, okay? But there are pieces in the article. Well, one piece says more cars were sold this year in India than in China. Okay, so these are these two bars, right? Then you go back to your text, keep reading, and it says, oh, and sales in Brazil are expected to decrease less than Britain in the next year. These are just two other bars, right? So if you think about it, the user has to kind of go back and forth, read the text, think about these different inferences, and identify the elements in the bar, in the graph, where this information is represented, okay? So it's well known that for some users, dealing with this multiple different forms of information presentation can be difficult. And so my PhD student, Derek Token, is working on building a system that can track how the user is looking at the text and the graph, and use that highlighting mechanism that I showed earlier to highlight relevant elements of the visualization when the user has read the relevant part in the text, okay? And I'm happy to give you more information about this if you're interested. The third point that I had here, I won't go into any detail on that, but oh my gosh, never do this. Going back when you have a lot of animations. We have done work on predicting from gaze when a user is actually confused, because that would be a good trigger, right? When do you want to provide help? Well, when the user is confused. Doesn't matter if the user is low, high, doesn't matter why. But even just knowing that the user is not getting the information, it's a good trigger to start thinking about this user needs help, okay? So in the study here, we actually created a data set where we had information, data points for user confusion, and we built a classifier based, again, on gaze data that had quite good accuracies in predicting when the user was confused. So now we're gonna also we're working on embedding that in, especially in the work that I just mentioned that Derek is doing on the magazine-style narrative visualizations, okay? Now I keep doing my jumping around because I want to show you the last slide, which is it's the most important, where all the people who worked on this are acknowledged. I'm just delivering the speech, but the hard work was done by, these are 2 faculty members, computer science department, Giuseppe Carinini, James Hans is a perceptual psychology at UBC, and these are all the students and postdocs who have contributed to this work, so I want to thank them, and I want to thank all of you for your kind attention. Thank you. Right, right. So those results that I showed were kind of going in the direction that you just mentioned. So they can choose whether to opt in or opt out of having both or not, right? And for, in the way that the customization was implemented, that's what we found, that for some of them, even for those who customized, okay, there was an interaction effect with a couple of individual differences showing that for some of them, customizing was not a good idea because their performance in terms of, for instance, decision confidence was lower than users in their same space in terms of cognitive abilities that decided not to customize, okay? So when they do it by themselves, for some, things work really well. They somehow have a sense of what is working, what is going to work for them or not. For others, what drives the decision to opt in or opt out might be preference, but preferences don't always align what was best for you, right? You might like and say, okay, I like to keep everything around, and you're not realizing, for instance, that you're going in cognitive overload, as opposed to, oh, I think it's good for me not to have all these visualizations, but in reality, you're actually quite good, well capable of using both of them. So that's where understanding where there could be support from another entity that somehow knows something about you and can guide your behavior is something that is definitely important to look at. Is that, sorry. Sure. Yes, that is a great point. And even these user characteristics, why do I have to build classifiers to catch them? I could give them the psychology tests. Problem is, having time with your users beforehand is not always possible, right? If you think about these kiosks where the MetroQuest thing could be used, people go, they want to get, they want to get going, they want to see what's going on, they want to play with the system and move on to the next kiosk, right? So there is no way to give them tests on anything, right? So when it is possible, for instance, when you might be dealing with users that are going to use the system for a long time, and it's okay, and for sure what you're saying makes a lot of sense. In other situations, it's just not possible because of the logistics. So, yeah. That's right. If you have the time to do it in a way that makes sense and fits with the overall interaction, it's something that you could do for sure. However, you would have to find a good task that is predictive of what they would do then with the system, right? But definitely is, getting information up front, if you can do it, is certainly a way to go, as opposed to just relying on this, real-time models. If you can do it beforehand, it would be definitely something to look at, yeah. I see what you're saying. Yeah, that's a good idea. Possibly, yes. So again, these are all very interesting things that one can try, and they need to be explored, because how to do the customization or the adaptation is definitely not easy. And it goes back to this idea, okay, you can show them the first screen, you learn about how they process it, and maybe in the next one you do the personalization, which would make a lot of sense. Could also be difficult though, because users might be, they might expect it and they don't see it, and this is one of the main tricky parts of user adaptive interaction, that you kind of, the user is, now the term doesn't come to me, but it's not transparent, and the user gets surprised by things that they don't understand what they're happening, right? So it's a great idea, and we've been thinking, we thought about it, but anything needs to be tested really carefully, because there is always a possible catch, a possible drawback. But definitely this is something that one could do. Use the first screen to understand the user, and then do the adaptation in the second. So for instance, you could do the adaptation in the second, not by hiding right away, but like having some gentle suggestions, right? Looks like. Exactly, exactly. You could do it in a way that is not, and it's definitely something that it would be a good way to try and personalize, for sure. Yeah. Yeah. Approval? Oh, yeah. No, no, I mean, there's ethics related to all this, right? So we have permission. For the eye tracker? No, no, no. I mean, the ethics approval is for the full study, including, no, 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 absolutely. And the users know, right? Because you need to calibrate. For every user, you need to do a, like, 30 seconds calibration. So they know that their gaze is tracked, and there is always, like in the form that they're given, there is always they know that they can opt out at any time if they feel uncomfortable. I've never seen anybody, feeling, I mean, it used to be my first eye tracking work, had a head-mounted psychology, heavy duty, and it's only head-mounted, but it was a chin rest. Not very ecologically valid, right? The error, the error measurements were like super low. It was fantastic. You didn't have to worry about, oh, let's just discard the invalid data. It was all perfect, but obviously, Yes, it's something that, it's a great point, and is related to all these issues of we're tracked in so many ways, and do we want it, At least here, yeah, they're informed, and they can opt out. But, I mean, another part of of your question is how realistic it is that you can track, you can have eye trackers on this say, for MetroQuest interfaces, right? So right now it's not. So I have one eye tracker, and all my studies, are done running one user at a time, because I only have one eye tracker, because it's very expensive, right? There are some cheaper eye trackers, but they don't yet have the accuracy and performance of the high-end ones. But all I say, the way I answer this question is, this is research, so it's proof of concept. You want to know what is the potential of this kind of information, and then I have great faith in the people who are working on eye tracking technology, that in a week or in 2 weeks or maybe 2 years, they'll generate beautiful eye trackers that can be attached. They're portable. You put it on your screen if you want the eye tracker to work, and they like $20. Maybe this will happen in 10 years. I don't know, but eventually will happen, right? And but the point is the eye tracking information. It really is a windows to the mind, as the say goes. Right? So. Yeah. So the kind of research where they keep recording you all the times, or? Yeah. So I'm sure it could be done, and I don't know if they're doing it. I try to ignore. I try not to think about it. I'm like, whatever. It's gone. They're tracking me, so I'm not doing anything illegal, So it's a good question, but I don't know. But I definitely know that eye tracking technology is being heavily investigated by companies because they understand the power of being able to get information of what they're looking at, not just if you're looking at the screen or not, right? Which a webcam can already tell you, or if you're looking up or down, that a webcam can already tell you. But really fine-grained information of where you're looking, I'm pretty sure that can be of huge value in applications for e-commerce and so on and so forth. And I'm pretty sure that they are working on being able to get that information. So, yeah. Yeah, there's a lot of work done on using facial expressions for detecting emotions. And it's probably facial expressions is one of the main sources and most promising sources for that. And especially emotions related to also like confusion, frustration in educational settings. A couple of points. So not all interactions generate or trigger detectable facial expressions, right? If you're upset or frustrated, maybe you see it. If you're kind of, certain more subtle emotions don't transpire, and also depends on the personality of the user, on the context. There are situations where you're not showing your emotions because you don't want people to see them, right? So it's not always reliable. And also for the kinds of things that we're tracking, for instance, perceptual speed, visual working memory, I don't think necessarily for those kinds of characteristics, I'm not sure if we could get a lot of information from facial expressions. But for other modeling tasks, user modeling tasks, facial expressions and face recognition has been used, yes. And also sensors like physiological sensors, also for emotions, like confusion, for instance, which is very important here. You could detect it from some facial expressions, right? Absolutely. And some physiological sensors for confusion. It's more like if it's high-low valence that you get quite reliably from these sensors. But, sorry? Yeah, so the patterns in that paper that I showed, there is, yeah, it depends on how they're looking and some properties of the angles between saccades, because it changes as if you're following a very regular pattern, that's an indication that you're processing with a strategy in mind. When you start kind of moving around, that's when, for instance, the standard deviation of the saccades angle gets really high, and that's an indication that you're like getting a bit scattered. But yeah, yeah. Mm. So that's a good point. So for some people, okay, some people follow the gaze with the mouse, right? So you're looking and you're using it, you're reading, right? You don't need to click anything, but you're actually following. It's not everybody does it, and this research is mostly related to processing text. So mouse as a proxy for gaze is not reliable for many people. And I don't know of any research done on when you process a visualization if you use the mouse. So it's something that would need to be done to see if you could use, for instance, mouse movements as a proxy for lack of gaze information. We have the results on the confusion paper where we track confusion. We were trying to see if, so for instance, head distance to the screen, okay? You don't need an eye tracker to track that, like the webcam could do it, right? So we had head distance and another measure that did not need, no, sorry, it was head distance and pupil dilation. These are visualization independent. So if you have, these measures were also very good predictors of confusion, but pupil dilation, currently, you need a fairly high-end eye tracker to track it, okay? So if you need gaze data and you don't have gaze, in some situations you just cannot really do this kind of monitor, and then you would have to rely on having good customization mechanisms for the user to do their best, right? And we haven't done any, we haven't tried to use eye trackers on mobile devices, no. That's right. Exactly. So yeah, the features, the paper talks about what are the predictive features of that, and I think there is a correlation between sort of like distance, like if you're leaning as opposed to moving back, right? So yeah, yeah.
Great. Okay, so that was an exemplary sort of walkthrough of how you try and build a user model, validate it, start training classifiers. Cristina, thank you so much. That was
Yeah.